Welcome back everyone. In this lecture we will continue with some basic notions of graph theory. So first I will start with how to define incidence matrix and adjacency matrix of given graph. So let us fix some notations. So we will be actually only working with finite graphs. That means the number of vertices and number of edges both are finite. So recall graph is a triple which has the set of vertices, set of edges and the incidence function psi g. So now the cardinality of this v of g, let us denote it by nu, and then the cardinality of e of g, which is the number of edges, let us denote it by epsilon. So now we can actually label the vertices and then we can just label them as v1 etc v nu, and then the edge sets again one can label as e1 etc e epsilon. So now what is the incidence matrix? So incidence matrix is the matrix of size nu by epsilon size matrix. So whose rows are indexed by the vertices v1 etc v nu, and then the columns they are indexed by the edges e1 epsilon e1 etc e epsilon. So we have something like this. So we have v1 v2 etc v nu, and then epsilon e1 e1 e2 etc e epsilon. So now what will be the ijth entry of this matrix? So let us call this as mg, whose ijth entry is mij, where mij is the number of times that vi and ej are incident. So mij records the number of times that vi and ej are incident. So note that this number has to be either 0, 1 or 2. It is 0 if vi and ej are not incident, that means vi is not end of ej, and it is 1 if it is just once it appears, and it is 2 if vi actually ej is a loop at vi. Okay. So if we have vi and then ej, then this mij becomes 2 and vi just appears in ej, then mij becomes 1, and if it is not appearing anywhere, so then we have mij is 0. So that is what this mij actually records, and this is what called incidence matrix. So basically the incidence matrix of a graph is just a different way of specifying the graph information. It is a large matrix because it is a nu by epsilon size. So it kind of contains all the information about the graph. What is adjacency matrix, which is very important? For example, it is the spectrum of adjacency matrix and all studied lot in spectral graph theory. So the adjacency matrix it is of size nu by nu. So you have this adjacency matrix which is, let us say, denoted by ag, and the entries are given by aij. So this is of the size nu by nu. So where both rows and columns they are indexed by vertices. You have v1 etc v nu, and then we have v1 etc v nu. So this is where the aij entries are recorded. So what this aij records? So it is the number of edges joining vi and vj. So you have vi and then we have vj, and then you have like some multiple edges that are joining Vi, Vj, and then you record that in Aij. So, basically Aij is the number of edges joining I and j in G. So, that is what it records. So, like I said, adjacency matrices are very important. They record important information about the graph, and the spectrum of that, which are the eigenvalues of this adjacency matrix, that is indeed studied a lot. So, that is because, so this Aij, because it counts the number of edges joining I and j. So, it is symmetric in Ij. So, Aij must be equal to Aji. In particularly, we have this A of G is a symmetric real matrix. Indeed, it is it consisting of only integer entries. So, note that Aij is either 0 or positive natural number, and it is a symmetric matrix. Now, one can use a spectral theorem and then say that all the eigenvalues of the symmetric matrix, so they are real. So, now understanding that eigenvalues actually gives lots of information about the graph in particular. So, that is what studied in spectral graph theory. Okay. So, what are all the diagonal entries? So, the diagonal entries again Aii, which actually counts number of loops that are actually there at the edge I. Okay. It basically counts number of loops at Vi. Okay. So, the adjacency matrix again it will have some specific form depending upon the graph that we are working with. So, maybe I will leave this one small exercise that actually tells what happens to the bipartite graph. So, let us say G is a bipartite graph. So, then what one can do, one can actually order the vertices of G. So that there exists ordering of Vg such that when you look at the adjacency matrix of G, okay, note that the adjacency matrix and incident matrix both depend upon the order. Okay. So, once you change the order, again the matrix changed, but anyway the linear algebra tells like it does not matter much as far as like eigenvalues and all concerned. Okay. So, if we look at this matrix, you have an ordering or the enumeration such that the matrix adjacency matrix of this bipartite graph looks like this block matrices, where we have on the diagonal 0 and then you have some A12 and then A21, and where this A12 and A21 are related. So, basically they comes from this bipartition. You have this x and then you have this y and then you have only edges from x to y. So, because of that these the number of edges between the vertices of x, they are all 0. Again the number of edges between vertices of y, they are all 0. That is what corresponds to this diagonal blocks, and these opposite ones, they are just transpose of each other. So, where A21 is the transpose of A12. Okay. So, such information like one can get immediately by understanding the graph structure. Okay. Like I said, so one can also kind of get more information by looking at the eigenvalues. So, maybe let me state this exercise, it is actually bit harder exercise. Anyway, so assume that G is simple and the eigenvalues the eigen values of the adjacency matrix of G, they are distinct. So, if the eigenvalues are distinct, then we know from linear algebra that the matrix A of G must be diagonalizable. So, if in this case what one can say immediately that the automorphism group of the graph G, so that must be abelian. So, then the automorphism group of G is indeed abelian. What is automorphism group? So, automorphism group is nothing but you look at all possible isomorphism of G. Okay. So, automorphism of G is nothing but the set of all isomorphisms of G as a graph. Okay. Since we are only considering the simple graph, the isomorphism can be characterized as follows. Basically, instead of having a tuple theta and phi, theta is a bijective map from the vertex set to vertex set, and phi is a bijective map from the edge set to edge set. So, we can only have the following map. So, only theta is good enough. So, basically it consisting of all these theta. So, I am going to write it like this, where theta is a bijective map from Vg to Vg. It is a bijective map such that whenever two vertices are adjacent, since the graph is simple, like I said before, the edges are determined by the endpoints of the given edge. So, that means if u and v are adjacent, then that should imply, or if and only if theta u and theta v, that must be adjacent inside your graph. And this is the like natural characterization of isomorphism of simple graphs, and automorphism of G is consisting of all these bijective maps satisfying this property, and this is naturally a group with respect to composition, and that group we are talking about, that group is abelian. Okay. If you do not know these notions, then you do not need to worry. I just wanted to give one glimpse of like where the eigenvalues of this A of G plays a role. Something stronger about automorphism group can be derived just by imposing some conditions on the eigenvalues of A of G. So, that is what we are getting here. Okay. So, let us move on. So, now I want to define the notions of subgraphs and induced subgraphs and so on. So, let us start with subgraph. So, subgraph naturally it should be contained inside the given graph. So, in more mathematical term, so a graph H is called a subgraph of G, usually written as H is contained in G. This is how we write. So, if the following condition should be satisfied, the vertex set of H should be contained in the vertex set of G, because the entire graph H should be contained in G. So, that means the vertex set should be contained in vertex set of G, and the edge set again should be contained in the edge set of G. So, now the incidence function. So, you have psi H and psi G. So, psi H must be restriction of psi H must be restriction of psi G to E of H. Okay. So, if these conditions are satisfied, then you call H is a subgraph of G. So, note that this actually does not say like anything about taking all possible edges between given two vertices and so on. Okay. So, anything could be a subgraph as far as it is contained in G. So, it is a very broad definition. For example, if we take something like this E, F, D 1 comma 2, then this just F 1 comma 2 is actually a subgroup of Gs. Okay. So, this is slightly different notions. Even this contains this vertex 1, this is also a subgraph. Suppose if you include one loop here, so then you can see that this is contained in this is contained in this, and this is also contained like this. So, all possibilities are there. So, all of them are contained in this. Okay. So, we say that H is a proper subgraph if H is actually not equal to G. So, H is called a proper subgraph of G if H is contained in G, but H is not equal to G. That case you call it proper. So, what is a spanning subgraph? So, spanning subgraph of G is a subgraph whose vertex set is same as vertex set of G. So, a spanning subgraph H of G is a subgraph with the vertices of H is same as vertices of G. Okay. For example, here, so this is a spanning subgraph and this is a spanning subgraph and so on. So, it already tells you that there could be many spanning subgraphs, that is not a problem. So, now what one can do, like you can start with the graph and then we can delete all loops and multiple edges. So, one can start with a graph G and delete the loops and multiple edges. So, you delete enough edges so that you reach only one edge between given two vertices, okay, and obtain a simple graph. Okay. So, you keep just if there are like more edges between given two vertices, you delete enough of them and then keep only one edge between them. If you find any loop, you just delete it. By this process, you can always obtain a simple graph whose vertex set is same as your original vertex set of G. So, that means we can always get a simple spanning subgraph of G. Okay. This process actually tells us how to get this simple spanning subgraph of G. So, usually that is actually called what is called underlying simple graph of G. So, simple spanning subgraph of G is also called underlying subgraph of G or simple graph of G. So, these are all some notions that are actually used in graph theory. So, there is another important notion called induced graph. So, let us define that. So, induced graph is slightly stronger than subgraph. So, induced subgraph. So, what it is? Let us first look at vertex induced subgraph. So, let us take V dash to be a subset of V. So, where V of G is actually a vertex set of given graph G. So, now what we are going to do? We are going to look at the subgraph of G whose vertex set is V dash and whose edge set is the set of those edges of G that have both ends in V dash. Okay. So, you look at so basically what is my G bracket V dash. So, G bracket V dash is consisting of V dash, that is the vertex set, and then you look at the edge set E dash and xi g bracket v dash, okay, which is the restriction function. So, what is this E dash? So, E dash consists of all edges from G whose both endpoints are in V dash. So, such thing actually you call it as induced subgraph of G induced by this V dash. So, this is a very important notion. Okay, let us look at some example. Let us say I have a graph something like this. So, now if I have these vertices, let us say label them like this. Let us not worry about labeling of edges. So, now if I take for example 1, 2 and 4, 1, 2 and 4, and then I look at the subgraph induced by this, then what is it going to be? So, it should contain all the edges that are actually having the endpoints coming from this 1, 2, 4. So, then it should have this, this and this. So, it should look like something like this. You have 1, 2 which is there, and then 1, 2, 4 is there, and then again another 2, 4 is also there. So, this is the induced subgraph. So, you do not take everything that actually goes out of 2, you just simply take those edges which has both endpoints coming from this subset V dash. So, similarly one can actually talk about induced subgraph induced by subset of edge set. So, one can actually fix E dash subset of E of G, and then one can talk about G E dash G E dash. So, it is the induced subgraph of G induced by E dash. So, what is this? So, the subgraph, this is the subgraph of G whose vertex set is the set of end points of edges in E dash. So, you look at all possible edges in E dash and then take the end points of that, and whose edge set is now fixed. So, that is E dash. So, only V dash we need to define. So, V dash is the set of end points or ends of edges of E dash. So, that you take to be your V dash. Now, the incident function of this is going to be the restriction of the incident function of the original graph. So, this is what called induced subgraph of this. Okay, so, we can also actually talk about induced graph induced by the complement of V dash. So, which is usually denoted by V bracket V of G difference V dash. So, sometimes when you are actually just deleting one vertex, we just simply denote it by G minus V. So, what is G minus V? You start with the graph G and then you delete the vertex V, and then you delete all the edges that are incident to V. Okay, this is the vertex set is given by V difference V, where V is vertex set of G. The edge set of this G minus V is going to be all edges of G that have end points different from V. So, that is what G minus V. So, similarly one can define G minus E. So, you delete that H and then you keep rest of the graph. So, that is what G minus E. So, let us do one example. Okay. So, if we take a graph like this, say 1, 2, 3, 4, 5, and then let us say I want to delete this vertex 5. So, if you delete this vertex 5, this is let us say G, then G minus V will look like you have this 1, 2, 3, 4. So, this is my G minus V. And similarly, let us say I want to delete this edge E, then G minus E will look like you keep everything except that edge. So, this is called G minus V. Again one can also add one edge. So, you can talk about G plus F. So, what is G plus F? You take G and then just add something there. So, for example, if I add this, then that is called G plus F. You just add an edge. So, one can add multiple edges to given graph and then we can get a new graph out of it, and then that we can just write it as you are adding edges to given graph, okay, like this and then like this, etc. Okay, so this actually defines these notions of adding and deleting. So now what will be the disjoint union? So we can talk about, like, if I have G1 and then I have G2, then we can talk about the disjoint union of G1 G2. So basically what is this graph? You simply take the vertex set of this to be the vertex set of G1 union vertex set of G2. So it is a disjoint union, and similarly the edge set of this union is going to be the disjoint union of the edge set of G1 and G2. And obviously the incident function naturally extended to this disjoint union. So you have G1 here and then you have G2 here, you simply draw them together, so then you get this disjoint union. So note that one can actually have multiple copies of same graph. Okay, so for example, if I take some triangle like this 1, 2, 3 E, F, D, then we can talk about disjoint union of same graph. So then we will have multiple copies of same thing. So I can also have 1, 2, 3 E, F, D. If you are actually not comfortable with using the same label, what one can do, one can just use the dash to denote this new graph, and we can talk about any number of multiple copies, and that defines this disjoint union of graphs. So one can talk about union of graphs inside given graph. So let us say I have G1 and then G2, both are sitting inside G. So then one can talk about the union of these two graphs. Okay, what it is? The union G1 union G2. So it is basically the subgraph with the vertex set V of G1 union V of G2 and the edge set E of G1 union E of G2. That's all. So the vertex set is going to be V of G1 union V of G2. So the union G1 union G2 defined by, and then the edge set is just edge set of G1 union edge set of G2. So it not necessarily disjoint, it can be any subgraphs of G. So then we are defining the union of them, that's all. So for example, we can take something like this. So 1, 2, 3, 4. So now what one can do, one can take G1 to be just this 1, 2, 3 and then G2 to be just this 2, 3, 4. So, then the G1 union G2 is going to be just G. Okay. So, that is what defines this union. So, now if they are disjoint, then we can sometime write this notation G1 plus G2. So, this is like that internal direct sum and external direct sum. If G1 and G2 both are subgraphs of G and G1 and G2 are disjoint. So, what is the meaning of that? That means the vertex sets are disjoint and the edge sets are disjoint. So, then the union is denoted as G1 plus G2. So, it is just a notation. So, that is used in graph theory. Again, one can also talk about intersection. So, the intersection is again naturally defined subgraph of G. So, let us say G1 and G2 are given subgraphs of G, then the intersection what it is going to be? It is going to be the intersection of the vertex set. So, this is going to be the intersection of the vertices and the intersections of the edges. So, what are all edges that are common between them, then you just take those edges. But to define intersection, one need to have at least one common vertex between them, otherwise the intersection becomes empty. So, then we can't actually we can't have this notion. Okay. So, these are all actually summarizes some basic terminologies that are used in graph theory. So, we will stop here and then we will continue with some basic theorems like handshake theorem and so on in the next class. I will stop here. Thanks.